Hello, this is my first video. Welcome to Maths with Cats. So today we're going to be going over the first session of maths, and that is going to be proof. You may be wondering where the cats come in. The cats come in every other slide. So every time we have a slide of maths, you get to see some to relieve the stress of all the maths. So let's get on with some actual maths now. So with proof, the first thing you need to know is notation. Notation is important because it's quite often used in questions and occasionally you'll be asked to use it in your answers. So, set. What is a set? Set is a collection of elements shown using curly brackets. The definition for elements is later on. We'll go into more detail with set. So, it's often represented by a capital letter. So it might be the set A, and then it'll give you some more information. So it can be written in a few ways. The first way is as a list. So here, I'm sure you can figure out what list this is. It's the positive even numbers up to 10. So that is the first way of writing a set. Notice how it's got the curly brackets that we mentioned at the top. Oh, let me just get my laser pen out actually so you can see what I'm pointing at. So yeah, it's got the curly brackets mentioned at the top, and you can see it's a list with numbers with commas in between. A rule, well, again, you use the curly brackets, but you say what the rule is. So positive even numbers up to 10. It's the same set as this, it's just written in a different way. This one's a different set. So this is set notation, and this is an inequality in this case. So this is the set of values of x where x is less than 0. Just another type of set. So what is an element then? We mentioned element up here. What is that? An element is an object or a number in a set. So here 2, 4, 6, 8 and 10 are all elements within this set. Okay, so these are things you may want to use in your working sometimes. Sorry if you can hear that squeaky noise, it's the weird air freshener we've got and it's running out. So A arrow towards B. That means A implies B, or if A, then B. Just different ways of saying the same thing. We will use these in some working. I'm not sure whether in this video or I know we will use it in a video. A, and then this arrow that points both ways, B. A implies B and B implies A, or if and only if A, then B. Okay, just to know, you can have this but with the arrow pointing the opposite way, so from B towards A, that would just mean B implies A. So the arrow can point in either direction. This one, you should be able to figure out, it's fairly self-explanatory, not equal to. This is roughly equal to or approximately equal to if you want to use nicer wording. And in equals, but it's got 3 lines, identically equal to, so it's true for all values. Now, I will go into some more detail of that. So, identically equal to, I struggle to get my head around at first because it's like, well, what does that mean? It's quite often used in algebra. So let's say difference of 2 squares. So A plus B times by A minus B. Well, that, as we know from GCSE, is identically equal to A squared minus B squared. Now, I promise you my handwriting isn't this untidy in real life. I'm using a laptop pad to write that, so It's not the best. You can tell what it says. A plus b times by a minus b is identically equal to a squared minus b squared. That's the sort of situation you'd use this notation. Okay, so let's move on. This is another cute cat laid on a calculator. Very cute. I should say as well, none of the cats belong to me. Sorry, my laptop's taking a while. I think it's getting a bit confused. Yeah. None of the cats belong to me. I have gone on the online section of pictures on PowerPoint to find them. However, if I get enough subscribers, I've not decided on a goal for that yet. I will do a PowerPoint where I use a picture of my own cat. I have one cat called Spooky. We can talk about that more when we see some more cats. Proof by exhaustion. So this is the first type of proof we're going to talk about. Split the proof into different cases that cover all possible situations and prove separately for each case. Well, what does that actually mean? So there's different cases you could split it into. You could split it into odd and even numbers, and so you can prove that the statement is true for odd numbers and prove it's true for even numbers. Maybe positive and negative numbers, depending on the question. There's lots of different situations you could split it into. So let's have a look at an example. Prove that n plus 1, all cubed, is more than or equal to 3 to the power m for, and this means all natural numbers, and n is less than or equal to 4. I'm going to get my laser pointer back out. So, this is all natural numbers. All the natural numbers that are less than or equal to 4 are 1, 2, 3, and 4. There's no other numbers involved in that. So, we know that those are our cases. So, numbers can also be cases if there's a very select amount of numbers. So, 1, 2, 3, and 4 are our cases. So, when n is equal to 1, n plus 1 cubed, well, that's going to be 1 plus 1 all cubed, which is 2 cubed, and 2 cubed is 8. 8 is more than or equal to 3 to the power of 1 because 3 to the power of 1 is 3. So, it's true when n is equal to 1. So we've proved it for our first case. Our second case, n equals 2. Well, 2 plus 1 is 3, 3 cubed is 27. 27 is more than or equal to 3 squared because 3 squared is 9. So it's true for n equals 2. When n equals 3, well, 3 plus 1 is 4, 4 cubed is 64. And 64 is more than or equal to 3 cubed because 3 cubed is 27. Yeah, 27. I had a bit of a brain fart then. So, it's true when n equals 3. And when n equals 4, 4 plus 1 is 5, 5 cubed, 125, and that is more than or equal to 3 to the power of 4, because 3 to the power of 4 is 81. So it's true when n equals 4. So what does this mean? We've proved it for all possible situations, because it gave us this specification in the question, but it's for natural numbers when n is less than or equal to 4. So we've proven that the statement is true for all values of n where n is a natural number less than or equal to 4. So that might have taken a lot of concentration if that's the first time you've done proof by exhaustion, so I thought I'd show you a cat that is Okay, the next proof we are going to try, proof by deduction. It's also called direct proof or proof by direct argument sometimes. All the same thing, just given different names. So, for this one, we're going to use known facts to build an argument which shows the statement is true. So, here's an example question. Prove that the product of two rational numbers is always a rational number. Okay, so we need rational numbers. So we're going to let one be A and another one be B. So these are two rational numbers. Because it's a rational number, it can be written as a fraction. So we're going to write it as A equals P over Q, B equals R over S. Now P, Q, R, and S must be integers for it to be a rational number. And Q and S must be non-zero because they're on the denominator of a fraction. Now, the question was asking about the product of two rational numbers. So we're going to do A times by B. And because we've used this notation here, AB is equal to P over Q times by R over S. So AB is equal to PR over QS. Because of what we spoke about before, PR and QS must be integers because they are the product of integers, because we wrote about this before. And QS must be non-zero because Q and S are both non-zero. Because if you're going to multiply two numbers and get 0, one of the numbers must have been 0. But Q and S are non-zero, so this can't be 0. So that's why QS is non-zero. So what does this mean? It means AB is the quotient of two integers. Quotient, something divided by another thing, to be simple with that. So this means AB is the quotient of two integers and has a non-zero denominator, so AB must be rational. So we've proved the original statement. So all we've done is we've used what the question has given us to put something together, and we think about the conditions that must satisfy to prove it's correct. Time for another cat. So before I was saying about showing my cat if I get enough subscribers, she's called Spooky, she's got a belly, she's cute. That air freshener is making a noise. So I think that's a good idea. Let me know what you all think about it. Let me know if the cats thing is actually something that people are interested in. Obviously, I'm just starting off at the moment, not expecting loads of views on this video. But yeah, let me know what you think. Okay, so the next proof is a disproof by counterexample. So this is technically not a proof, it's a disproof, but it goes in the proof section because it uses the same logic. Okay, so this one is probably the easiest proof because you're just finding one case where it's not true. That's it. That's all you gotta do. So, here's an example. Disprove the following. For any pair of real numbers, x and y, if x is more than y, then x squared plus x is more than y squared plus y. So we want to disprove that by just finding one example where it doesn't work. So if we're just finding one example where it doesn't work, there must be some value for where x is more than y, where x squared plus x is less than or equal to y squared plus y instead of more than. So have a think now, without testing anything, just what conditions might make a sign, less than or more than sign, different to expected. So my thought is one of them being a negative number. That quite often messes up signs. So, based off that, well, if we're going to have a negative number and y is going to be less than x, then it makes sense for y to be the negative number. So, let's try these numbers. X equals 2, y equals minus 4. Now, all AQA exam papers for maths at A level, you're allowed a calculator. So, if you're struggling, test it. Just think, okay, what's two numbers? Let's type it in on a calculator, see if that works. That's a simple way to do it. Okay, so x equals 2, y equals minus 4. 2 is more than minus 4, so x is more than y. So that one's worked. X squared plus x, well, if x equals 2, then x squared plus x is going to equal 6. And if y equals minus 4, y squared plus y is going to equal 12. So x squared plus x is less than y squared plus y because 6 is less than 12. Okay? So what does that mean? We found an example where x squared plus x is less than or equal to y squared plus y, and x is still more than y. So it's not always satisfying this. The statement is not true. And you might want to explain that a little bit more in the actual exam, just as a safety net, but I think that should be enough. Hey, so anyone who's got a cat, cats love playing with anything that you're giving more attention than them. This one's probably going to be the hardest to get your head around. So for this, proof by contradiction, you assume the statement is not true, then prove that this is impossible. You'll be given a statement, and then you assume the opposite. You then have to prove that the opposite of the statement is impossible. Because if the opposite of the statement is impossible, then the statement must be true. So we'll go for an example, because, like I say, it's hard to get your head around. Prove that if x squared is even, x must be even. So we're going to assume that this is not true. So there must be an odd number x, for which x squared is even. So if x is odd, it can be written as 2n plus 1, where n is an integer. Because 2n is a multiple of 2, so it must be even. And any even number plus an odd number, 1 is an odd number, is odd. So x is equal to 2n plus 1. I realise I'm saying so a lot, so I'm going to try and avoid that. And, okay, so, I just said it again. X squared must therefore be 2n plus 1 all squared, if x equals 2n plus 1, which gives us 4n squared plus 4n plus 1. That's what x squared equals. Now, 4n squared plus 4n can be written as 2 lots of 2n squared plus 2n. So 4n squared plus 4n is even, because it's 2 lots of an integer. Which means that 4n squared plus 4n plus 1 is odd, because it means that must be an even plus an odd. So we have shown that if x is odd, then x squared must be odd. But we've assumed that there is an odd number x for which x squared is even. We've just disproved that. So that means that the original statement must be true. If x is odd, then x squared is odd. So if x is even, x squared must be even. This is an accurate picture of how much I was concentrating when trying to figure out how to put the plot together. Okay, so I hope you enjoyed that and found it useful. Let me know what you think about the cats thing. I thought it was a little twist on it and made it a bit more enjoyable. Okay, thank you for watching.